to talk about chemical nomenclature, naming compounds. And specifically, we're going to focus on a type that is within the ionic category and consists of only two elements. Together, we call those the binary ionic compounds. First, you might wonder, why do we have to bother naming chemical compounds? Well, students, if you think about it, chemists all over the world need to be able to talk to each other. Chemistry is an international pursuit, and a chemist working in Germany needs to be able to talk to a chemist anywhere else, Japan or Australia or the United States. So we've developed a system for naming chemical compounds so that we can all be conversant in what we're talking about. Nomenclature is a fancy word for a naming system. And when we're talking about chemicals, we're talking about a naming system for chemical compounds. The idea here is nomenclature allows scientists to precisely communicate with each other around the world. Okay, so we're going to start with what is typically considered the simplest type of compound, binary ionic. The word binary suggests that there's two things. Bi means two, and that is absolutely the case here. Binary compounds have only two elements in them. And specifically, we're going to talk about ionic compounds. Now, the nature of the difference between ionic and the other type of compounds called covalent is very important, and it's somewhat complex. But for right now, at the most rudimentary level, we can get by with just remembering that ionic compounds consist of a metal element combined with a non-metal element. And if you can remember that along with the position of metals and nonmetals on the periodic table, with particular reference to that stair-step line or zigzag line that cuts between boron and aluminum, we're going to be just fine. The other type of compounds that exist that are relevant to nomenclature are the covalent type, which consists of the combination of two or more nonmetals, which kind of begs the question, what about two or more metals being together in a compound? That does exist. They call it metallic compounds. It's usually beyond the scope of a general chemistry course, but for right now, we're going to focus just on ionic compounds that consist of two elements. It's really important to know the trends for charge of the ions in the periodic table. Now, we're going to get a much better understanding for why these charges are where they are on the periodic table in Unit 4. But for right now, I do need you to actually take your periodic table, and at the top of column 1, I want you to write +1, because the elements in that column, when they form ions, most often, and when I say most often, you can think of that as meaning always in this course, form a charge of +1. Column 2, +2. If you remember the transition metals, the elements kind of in the middle, they have various charges or variable charges. There are some exceptions. Silver is a transition metal, or it's in the transition metal block that has a stable charge of +1. And zinc and cadmium on the right side of the transition metals also have stable charges of +2. So, but even though they're within the transition metal block of the periodic table. Other elements that you should be aware of, column 13 has a +3 charge. Column 14 almost never forms ions, so we just leave that column blank. By the time you get to column 15, there's the easiest way to fill the outer shell of electrons for these atoms is to add more electrons, which makes the charge negative rather than positive. So the nitrogen column, column 15, forms -3 ions. The oxygen column forms -2 ions. The halogen column -1. And the noble gases, they don't form ions at all. Again, they don't even combine. They're zero charge. Okay, that's super important. Let's consider some general principles. In an ionic compound, the ions will combine in a ratio that makes the compound neutral. That means the sum total of the positive charge has to be equal in magnitude to the sum total of the negative charge. So take Na, that's sodium from group 1, that's the column on the left. that would form a +1 charge. Chlorine, group 17, the halogen column, forms a -1 charge. Well, one atom of each just cancels out each other's charge to make a neutral compound, NaCl. So one atom of Na and one atom of Cl cancel out and make a net charge or overall charge of 0. So 0 overall charge. Let's try a little more complicated one. How about magnesium combining with chlorine? Now, the first thing you're going to want to do is to locate those elements on the periodic table. So hopefully you have your periodic table nearby. Go ahead and look up and find magnesium, and look up and find chlorine. You'll find that magnesium is in column 2 or group 2, which means it's in that column that takes +2 for its charge. Chlorine, column 17, takes a -1 charge. So if we think about that, we've got to make the compound neutral overall. One atom that's double positive would take 2 atoms that are each single negative in order to make it neutral. Hence the formula Mg implied subscript 1 Cl2, or most often that's written MgCl2. How about lithium combining with nitrogen? Take a moment to find lithium and to find nitrogen on the periodic table. Lithium's in column 1. That column takes a +1 charge. Nitrogen's in column 15. That's the column that takes a -3 charge. So one atom of -3 charge would require 3 atoms of lithium, each of which are single positive, to give an overall formula of Li3N. It's not always the case that you need to have a subscript of 1 for the first element in a binary ionic compound. You might have a subscript of 1 for the second element. Okay, one other thing that's important to remember are those the 3 transition metals that are with a stable charge. So generally speaking, we have to give a Roman numeral when we encounter a transition metal in the name of a compound. And the size of the Roman numeral corresponds to the charge. Now, you don't know that charge necessarily until you see what it's combined with. I'll show you what I mean in just a moment. These 3 transition metals, or I should rather say elements in the transition metal block on the periodic table, do not require a Roman numeral because the charges on their ions are consistent. Conversely, there are 2 elements that are outside of the transition metal block of elements who do require a Roman numeral because their charges on their ions vary, and they are lead, which can carry a 2+ charge or a 4+ charge, and tin symbol is Sn, which also can carry a 2+ or a 4+ charge. So these non-transition metals do require a Roman numeral. These elements which are in the transition metal block do not require a Roman numeral. Let's try some practice. There are a lot of rules to remember here. If we were to ask, I've got on the left side compounds whose names we're asked to write, and on the right column we've got compounds whose formulas we're asked to write. So KBr, let's see. If we're thinking about KBr, on your periodic table, you're going to look for the K for potassium. And you're going to notice that it's in column 1, and it would therefore have a +1 charge. Br is bromine, and it has a -1 charge. It's in column 17. So putting that together, 1 atom of potassium with 1 atom that's bromine, you would just call this compound potassium bromide. We and we changed the ending to "ide." Ni, that stands for nickel. I'll give you a second to look for nickel on the periodic table. Look in the transition metal block. Ni. It's towards the top of the transition metal block. It's element number 28. When we pair that with bromine, which is a 1 minus charge, we notice that it takes three bromines to cancel out the charge on one nickel. That means that nickel's charge, which is variable because it's a transition metal, would have to have been a 3 plus. If it's a 3 plus, then when we name it, we write nickel, parentheses, Roman numeral 3, close parentheses, bromide. So nickel 3 bromide. These next two are really interesting. FeO. Fe is a transition metal. I'll give you a second to find it. It's two elements to the left of the nickel, element 26. So again, it's a transition metal. We're going to need a Roman numeral when we name this. But what Roman numeral should we give it? Well, we have to look at what it's paired with. Oxygen is paired with the iron in this case, and in a formula that takes one atom of each. So one iron cancels out the charge of one oxygen. Okay, find oxygen on your periodic table and note the charge for that column. It's a -2 charge. So if oxygen is always -2, and iron can sometimes be various charges, in this case, the iron had to be +2 because it canceled out the charge on the -2 of oxygen. So we call this compound, that we name it iron, Roman numeral 2 in parentheses, oxide. Now contrast that with the next one down. Here it's still the same elements, iron and oxygen, but this time the formula is Fe2O3. Okay, if it's Fe2O3, that means two atoms of iron of some charge we don't know pairs with three atoms of oxygen whose charge is always -2 because oxygen's not a transition metal. It's always got the -2 charge. I'm going to do a little bit of mental math here. Three atoms that are each double negative gives a total of 6 units of negative charge. That means that the iron, in order to make a neutral ionic compound, had to have provided 6 units of positive charge. Well, if we needed 6 units of positive charge altogether, and it took 2 atoms of iron to provide that, that means that each iron atom was a +3 charge, half of 6. So this compound's name is iron, Roman numeral 3 in parentheses, oxide. Notice that the difference between the previous compound's name, iron 2 oxide, and this compound's name, iron 3 oxide, is just a difference of 1 in the Roman numeral, and yet it provides a different looking formula. And I can tell you that the properties of these two compounds are vastly different. So a difference of 1 in the charge makes a tremendous difference in how the compound behaves. Last one on the left column, ZnF2. Here we have zinc. Now, zinc was one of those exceptions. It was an element in the transition metal block that has a stable charge. You need to have memorized that element's charge. There's only 3 that I need you to know. Silver's +1. Zinc and cadmium are each +2. So a zinc atom that's +2 would have been canceled out in charge with 2 atoms of fluorine. If you find fluorine on the periodic table, you see it's in column 17. If each element of fluorine bears a -1 charge, that would just cancel out the size of the charge on 1 zinc, hence ZnF2. And this time, because zinc has a stable charge, do not write a Roman numeral. This compound's name is simply zinc fluoride. No Roman numeral in the middle. Now let's write formulas. Here are the names. Lithium fluoride. Here's where you've really got to look up on the periodic table and note the element's charge for its column. Lithium is in column 1. That's +1. Fluoride, well, that's the "ide" ending for fluorine. Fluorine's in column 17. That's a -1 charge. So a +1 lithium and a -1 fluorine, they would pair in such a way as to have one atom of each, making a neutral compound. So the formula is simply LiF. If you prefer to write the subscript 1, Li1, F1, you could, but it's not necessary, and most chemists don't do that. Next one, calcium sulfide. Sulfide is the "ide" ending for sulfur. So we're going to look for calcium and sulfur on the periodic table. Note which column they're in and the charge for those columns. Calcium's in column 2, so it carries a +2 charge. Sulfur, column 16, it's right below oxygen. That's the column that has a -2 charge. Now, don't get confused. Just because the magnitude of charge is 2 does not necessarily mean that you have a subscript of 2 in the formula. What you're really asking is how many atoms of calcium pair with how many atoms of sulfur to make the charges balance. Well, it's a +2 and a -2. They're already balanced. So one atom of each, CaS, is the formula for calcium sulfide. Next one, cobalt Roman numeral 3 fluoride. Now, why did they need to put the Roman numeral 3? If you look to find cobalt on your periodic table, it's element number 27. It's at the top row of the transition metals. That means that column does not have a stable charge that you can just look up. So they had to have told you that its charge is 3. The Roman numeral 3 tells you the size of the charge of the positive ion. So cobalt with a 3+ charge is going to pair with, I see fluoride. Well, that's fluorine with an "ide" ending. Look for fluorine in column 17. It's at the very top. So we've got a -1 charge for fluorine. One atom of cobalt that's triple positive requires 3 atoms of fluorine, which are each single negative. So the formula for cobalt 3 fluoride is COF subscript 3, COF3. Titanium 2 oxide. Titanium, that's a fun one. Notice it's a transition metal, and therefore they had to give you a Roman numeral 2. That means the size of the charge on the titanium ion is a 2+. And oxide, well, that's oxygen with the "ide" ending added. Oxygen is always a -2 charge. So one atom that's double positive pairs up with one atom that's double negative. Just like calcium sulfide took one atom of each, titanium 2 oxide also takes one atom of each. So our formula is TiO. TiO. Last one, silver bromide. Silver bromide. Find silver on the periodic table. Look in the transition metal block. It's element 47. Now you might say, they didn't give me a Roman numeral here, so I can't do this one. Students, there are 3 elements in the transition metal block that have stable charges. You have to be able to memorize them and recognize them. Silver is one of them. Silver always takes a +1 charge. Bromide, well, that's bromine with an "ide" ending. Bromine, look in the halogen column, column 17, that's the -1 column. So one atom of silver with a +1 charge would pair with one atom of bromine with a -1 charge to give us the formula Ag for silver and Br for bromine. Simply AgBr, no subscripts needed. Thanks for listening. Good work.